as you all probably all know, ROUGOL's meetings are all free. We never have any charges, but obviously the Zoom is costing us money. So I'm just going to post a link in the chat to our PayPal account. If anyone wants to bung a couple of quid in there, that's all it needs to be, just to help pay our Zoom for the next year. Please feel free. Oh, wrong key because it's changed. Obviously, that particularly applies to those on Zoom because the meetings here in the pub are luckily free. Right. Okay, I think that's all I've got to say. I'll now hand over to Jeff, who is going to completely blow our mind with 64-bit stuff, no doubt. So, all yours, Jeff.
Thank you very much. Let me go and share the screen for my slides. Here we go. Right. So, did that work? I'm guessing it did. Yes, looks like it has.
Yes, it did.
Excellent. Right. So, I'm going to go and talk a little bit about 64-bit. And I would very much like people to get involved and to try and offer their thoughts, their opinions, their disagreements with me, or agreements. I mean, that can happen too. So that we can all try and find something that we can actually do about 64-bit. I'm not giving you any answers. I'm not going to give you any, you must do it this way. But I am going to be talking about some of the different things that are related to 64-bit. So I'm going to talk about in a number of different stages. I'm going to talk about what it is, how it's different to 32-bit ARM, the one that we all know and sometimes love. We're going to talk about what problems that 64-bit migration will cause, and how I think we can address those things. Now, there's been a lot of discussion about that, and my decisions and my thoughts on the matter aren't the only ones. They're just my possibly considered, sometimes erroneous things, but they're my thoughts. We'll have a look at some actual 64-bit code. I'm going to say 32-bit when I mean 64-bit a lot of the time, I'm sure, because I just get confused. I'm still thinking, oh, 26-bit is the current and 32 is the new and fancy. No, I get confused. So don't worry too much if you think, oh, I was talking about the wrong thing. I really am almost always talking about 64-bit, except where I explicitly say 32, he says. And then finally, we'll have a conclusion, which will be very nice and short. I'm going to be talking about the ARM architecture, the instructions, the memory, the different model that it uses. Some of that may be quite technical. I'm hoping that I'll still be able to make it understandable to people. And if I can't, jump in, say something, post something on the chat if you want to. There's probably a little raise hand button somewhere. I can't see, I don't have one, but you might have one, to get my attention and what have you. So without further ado, let's move on to the first section. First section is, who am I? So I've tried to introduce myself every time we do these things, but I'm Charles. I go by Jerf most of the time. I've worked for RISC OS Limited. I produce RISC OS Select with a number of other people. I've ported a good chunk of RISC OS to be 32-bit during that time. I've also written RISC OS Pyromaniac. I've worked with RISC OS for many, many years, too many years. And I am always an advocate of actually changing things to make them better, to move things forward, not just keeping things staying stagnant, not keeping them the same as they always have been. I'd like to keep things working if at all possible. 64-bit is going to break everything. That's just inevitable. But where we can, try and keep things familiar. I think if you remember, the migration from 8-bit to 32-bit was obviously a massive change, and that was handled reasonably well by Acorn. They provided a number of emulators to make things work and the like. That could be done as well. I'm not going to talk about the emulation of 32-bit or the coexistence of 32-bit with 64-bit. I think that can be a whole separate thing, and it's something that needs to happen, I think. But I'm just going to talk about 64-bit itself for now. So let's first talk about what 64-bit really is. We have 64-bit ARM was introduced in, I think, V8, might have been in V7, but this is what I remember anyway. And it has a backwards compatible 32-bit execution state. That means that you can run, optionally, 32-bit instructions and switch between it and the 64-bit state. And the 64-bit itself refers to both the size of the memory that can be addressed and the register size. It also refers to a bunch of features that come with it, like implicit vector floating point and a few other things. They just come with the with that architecture. So I've said it strictly. ARMv6 defines ARC64 and ARC32, but we've got a lot more in V8 and later, and that's where it really matters. I'm going to use 64-bit ARM and ARC64 interchangeably. You'll see them used on the internet in common ways. ARC64 is just awkward. I try to use it because that's the correct term, but yeah. And the same goes for 32-bit. I may just say ARM, I may say 32-bit ARM, or I may say ARC32. Again, they mean the same thing. So, why should we care about this? Well, as you probably know, 32-bit is going away. Future iterations of chips will not support 32-bit execution state. And RISC OS only works in 32-bit. And that means that it will just stop having chips that can run it. I mean, you can still run emulators, that's fine. But you won't have the, on real hardware of running it with 32-bit. So that becomes a problem. And it's something that you've really got to try and address and at least think about, because if you don't move with the times, you're going to be left in the background, left in the dust, and not be able to do anything. An operating system that just goes nowhere. I mean, strictly, there will still be 32-bit chips around, just like there are 6502s you can still buy these days. But it's not going to be the fastest things. It's not going to be the best things. They're just going to be legacy things that are produced to meet requirements. So let's look at how it's different to 32 bits. Now, I'm going to be spending a lot of time comparing the two, or a bit of time comparing the two, and talking about the actual architecture. Again, pick me up if I have gone and got something wrong, or I've not finessed it quite right. I'll be making some generalizations, obviously, but there are some things that I may just get wrong. My understanding of 64-bit is not complete. My understanding of 32-bit is not complete. And there will be other people who know more than me. But I'm going to talk about it. So hopefully that gives me a little bit of authority. We'll see. So first thing to talk about is the instruction set. So 32-bit, as we understand, has 32-bit wide instructions, or 16 or 32-bit wide thumb and thumb 2. We all know that conditional instructions are a big feature on most ARM. There are some instructions that aren't, and that's how the instruction set has been expanded. And we also know about the load and store of registers in a single instruction, the LDMs and STMs. They're really quite useful. There are lots of other features that are in there, but those are the ones I'm just going to pick out right now. ARC64 still keeps 32-bit wide instructions, but it doesn't have a shorter version. There's no thumb. And that's largely because memories become cheaper, and trying to have shorter memory words just isn't as worthwhile anymore. There's also the instruction set not being compatible with 32-bit ARC32. That means if you try executing regular ARM, it will go and fail on a 64-bit execution state. Most of the time, usually almost all of the instructions that you might commonly execute will end up being undefined. And that's because some of the major patterns that are used in 32-bit end up being a undefined instruction in 64-bit, which is actually quite cute. Makes it quite interesting. But also, there aren't any general conditional instructions, so you can't have condition flags on everything. There are a few instructions that have conditions on them, but you can't have simple or if not equal, and if equal, compare if greater than, although there is something similar. And you can't load and store multiples of registers up to 16. You can only store pairs of registers, which is a little bit more restrictive, but not terrible. Anybody want to give any other comments on instructions whilst we're on this?
I just wonder, does the barrel shifter still exist?
There are certain barrel shifters, yes. And there's actually LSL and LSR instructions rather than shifts on the instruction offsets. Limited barrel shifts are possible. So you've got LSL by the size of a word. So you're allowed to do LSL by 0 and LSL by 2 if you're accessing if you're accessing a 32-bit value, and LSL by 3 if you're accessing a 64-bit value. So that basically gives you word offsetted references. So if you're loading from an array of words, you can get those really easily, but those are special cases.
So it's mainly just intended for shifting 32-bit things into the right bit of a 64-bit register.
Yes, but there's also a very exciting OR instruction. So the OR instruction is able to set runs of bits in a word and then repeat them across the entire 32-bit or 64-bit value, which makes for a really interesting thing where you can set all the bits in the first byte, all the bits in the third byte, all the bits in the fifth byte, all the bits in the seventh byte, in just one instruction, which is really quite crazy, but really useful for certain manipulation operations. They've taken some ideas from what do you commonly have to do when you're manipulating things, and that actually works for, like, if you want to get every third bit, you can do that, or 3 bits at a time, or things like that. Really crazy, but fun.
Okay, thank you.
Okay, just briefly, what is thumb?
Thumb was, or is still, the 16-bit variant of ARM. It's basically a shortened version of the ARM instruction set. It only allows you access to 8 registers at a time. So you access R0 through to R7 and the stat pointer and PC, I think. And it was because it's only 16-bit, you could pack a lot more instructions into memory. And when memory was more expensive or slower to access, that meant you could actually get more bang for your buck. Basically, people inside ARM worked out what the most common instructions were that you were to use and allowed them to be used in Thumb as a subset of the system. And then you could run through that more quickly. And you could switch in and out of Thumb state at will, which was kind of nice. You'd commonly find a lot of embedded devices use Thumb because the amount of memory that was needed on ROM was much smaller. Does that make sense?
Thanks, yeah.
Yeah, no problem. All right, let's move on to memory. So, obviously, this is one area that is different. In 32-bit, you've only got 32 bits of logical space. That means that it's the system that we understand quite well. That's still quite a bit of memory, and physical memory can still be larger. There's a large page extension, which allows up to 40 bits to be accessed from the memory. So you can actually have larger memory on the system than 4 gigabytes that was just mapped in. And that's used by RISC OS 5, I believe, if you've got larger memory systems. It does, however, need a bit more intelligence and work in the operating system to access those. And the same logical space is used by all modes. That means if you're in supervisor mode, if you're in the different interrupt modes. If you're in abort mode, all of those are just the same as if you're in user mode, if I understand things correctly. ARC64 has a logical address space of 64 bits. That means you've got the full address space, but you can actually only access physical memory that's 48 bits. That basically means that you can't have 64-bit, which is, no, can't remember how much that is, 4 gigabytes times 4 gigabytes. That's a lot of memory. You can't actually put that much memory into a system or map that much memory. But you can actually have it as physical address, as logical address space. Anybody wants any comments about memory before we move on? Yeah, good. That's handy because memory is not very interesting. Although it does mean we get lots more packed in. Registers. Okay, so I think we probably all mostly understand what the register set is like on 32-bit. They're 32-bit wide, and we name them with an R prefix. There's also the stack pointer, the link register, and PC, which are regular registers. They're R13, 14, and 15. Okay, ARC64, they're all 64-bit wide, and the general name for them begins with an R. But they can be accessed as either 64-bit or 32-bit. So you'll commonly see registers referred to as X0, X1, X2, all the way through to X31, and W0 through to 31. So W0 is the same as X0, but just the low 32 bits of it. So W is closer to what we understand with R. And you can mix and match these. So you can load a value from memory using 32-bit with the W register, and then store it somewhere else with the X, and store it as 64-bit. And you can decide whether you want it sign extended or not. The stack pointer is a special register. It's not a numbered register. It's actually entirely separate, and it can be used in certain instructions, not all of them. It also has a limitation that it must be aligned to 16 bytes. So if you can imagine two registers are 8 bytes long, that explains why there's a load pair of registers and load and save pair of registers. That keeps the stack in the same to the same alignment. If you try to use the stack with a different alignment by configuration, that may abort. You may actually get an abort because the stack is no longer valid. And that's just to protect you from various things. Link register is a regular register. It's just by convention, it is X30. There's also a special register that does double duty as a 0 value. So that's commonly called XZR. And that's also the register 31. So X31, XZR are the same thing. Internally, that's also the stack pointer when it's used in certain cases. You don't need to know that, but it's being hidden away. So that's the main set of registers, but there are more details that are actually quite interesting. So in 32-bit, the floating point support was quite variable. The actual support is optional, and it's available in different forms on different chips. That gives you a little bit more confusion about what's actually available. The current processor state register, CPSR, and saved processor state register hold the current and saved processor states. And you've also got some others that are banked in different modes. In 64-bit, floating point support, if you support vector floating point, you must support a particular set of variants of that, which gives you a lot more reliability about what is going to be available for you. That means that providing software is easier. I suspect that it will be just pretty much there all the time because it's essentially just part of the system now. And the term for the processor state has been changed to P state. It does include the things that were in the CPSR, but it also defines that some parts are undefined. That's probably right, yeah. Things like the execution level, exception level, sorry, are actually in the processor state, but they're not actually guaranteed to be there. It just happens that they are in all implementations. So there's some interesting things there. There's also the save processor state, which is a special system register, like some of the other exception registers you might have seen on 32-bit ARM, like the fault address register and things like that. And the stack pointer is preserved in the system registers on exceptions. So when you get an exception, the stack is automatically saved. Okay, anybody want to give any comments on register state? No? Okay, let's move on to the calling standard. So these are so large, I've actually split them across multiple pages again, I'm afraid. So if you've written assembler that works with C, you'll recognize all of this. But if you don't, I'm sorry about that. So registers 0 to 3 are used for passing parameters, and then we use the stack for some extra registers. That's not very many registers to pass in, and so it's quite limited. You can see why we might be expanding the register set. Brian, were you wanting a question?
No, I was just reading the chat to see if there's anything important in it.
Yeah, right, sorry.
And it's fine.
R0 to 3 can also be used as the return registers. Commonly, you don't see that happening. You might see it happen when you're returning blocks of data, and you can force it with certain cases. If you ever used the divrem macros, you'll see that the return values in R0 to R3 are commonly used. R4 to R11 are preserved between calls. They're caller saved. R9 in some configurations is used as the static base. R10 stack limit, then the frame pointer, random scratch register in R12. And then we've got the stack pointer and the link register, which can also be used as a temporary register. All pretty simple, and we understand these, hopefully. Sorry, Simon Wilcox has just corrected me and said R4 to R11 are callee saved, not caller. You're correct, I apologise. That's what happens when you don't write a script. So, the second page, which I've also cunningly labelled calling standard number 1, is about 64-bit. So in 64-bit, we've got 7 registers that are used to pass parameters, and then you flow onto the stack. That makes things a lot easier for you to pass larger numbers of registers. There's less. Sorry, Vince has pointed out that 0 to 7 is 8 registers, because I can't count. And that 0 to 7, 8 registers, also used to return values, so we can return much larger things as well. And those are also corruptible between calls. R8 to 15 are also corrupted between calls. So if you want them saved, you've got to save them before you make a call. So that's half of your registers are corruptible between calls. All of the things higher than this are preserved. 16 and 17, however, can be corrupted because they're inter-procedure workspace. They're for setting up effectively the stack base, the global offset pointers and things like that. Also for handling dynamic loading and things. Those are a stash space that you can use. X18 is actually reserved for the system platform's use, the operating system's use. It changes between each operating system what X18 is used for. Some use it for the thread pointer, thread state. Others use it as some general workspace. So that's an oddity. You'll find that the compiler doesn't touch it most of the time. You can make it touch it, but generally you don't. And then the rest of them are preserved between calls. The frame pointer is now pretty much guaranteed by convention, and the link register as well. And the reason for that is because when you're passing between function calls, you're required to stack 2 registers because you've got to keep the stack 16 aligned. And if you're going to store 2 registers, you might as well store the frame pointer and link register. So you'll never find anybody that doesn't really do that, unless it's hand coded, and don't do that. And then, as I mentioned, X31 is the stack pointer and 0 register, depending on how you're using it. Like APCS, the flags are also corruptible across calls. Anybody want to make any other comments about the calling standard? Anybody want to point out the vector registers haven't been mentioned? Please don't.
Well,
Hi. Question from Mark.
Can you hear me if I ask a question from here?
Just about, yes.
Yes. I'm coming at this with a little less knowledge than you guys, I think. But this idea of the calling standard, that's how you sort of invoke an SWI call. So is it
not just SWI calls, not just SWI calls. This is largely for intercalls between functions in either user mode or system mode.
So the question is, how come this isn't really defined by the operating system? Because you're sort of saying this is gospel as defined by this processor. So what tightly couples it to the processor rather than it being a design of the OS?
So we can choose to do things completely differently. We don't have to follow the calling standard here. That is entirely true. However, if we do that, we make our lives difficult because it means that we can't use the standard compilers. It means that we can't interwork with things that have been created by other people.
Yeah.
So it is a strong recommendation. I will talk about the recommendation I have for SWI calls very shortly, but it fits very closely to this calling standard because I want to be able to make things as easy to use with the different compilers. As I say, we could choose to set things up pretty much exactly like we do on RISC OS at the current time and have stack limits. We could set up using the bottom of the stack as a bounce point when we use supervisor mode, system mode, and things like that. But I don't think it's a good idea, and that's why I'm talking about this as a calling standard. That's the generally accepted way that ARM say, if you do it this way, stuff will interwork well.
Yeah, so there's nothing in hardware that ties you to doing it this way, but logically, like I was saying, if you want to be compatible with existing software from other platforms, you're suggesting. Yeah.
Yes.
That's my takeaway. Okay, thank you.
With the one exception that X31 is always 0 or stack pointer. That is hardware.
Yeah, so there's a couple of restrictions, but yeah.
But otherwise, yeah. Okay. All right.
One other question. Am I correct in remembering that? Am I correct in remembering that RISC OS on 32-bit ARM uses a slightly different version of the call, slightly different version of the calling standard compared to modern Linux, for example?
My understanding is that yes, it does. I have not spent enough time working with the lower level how Linux uses it, I'm afraid. In particular, we have a stack limit that we in supervisor mode. We have a stack limit that is handled differently, and we have magic values at the base of the stack for that code. We also have the possibility of using reentrant code, which was a somewhat old definition that ARM created and has been abandoned by everybody. If you use mine is APCS 3/reent, you'll see that, and that allows you to use a separate register for it. That was the R9 that I alluded to earlier. Nothing of that even exists, and I don't believe it's used by any other system but RISC OS, except that RISC OS doesn't actually use it. It's only the compiler that can create it. However, again, I could be wrong on that because I haven't looked at how a lot of the Linux things work, I'm afraid.
Mm-hmm.
Okay, does that answer your question?
I think so.
Okay, cool. I shall move on to the next page, which is about the privilege model. So I'll just quickly cover what the privileges are. So in most systems, you have different types of different modes of operation. There's the user mode. That's where most of the things that we run as users will live, your applications are like. Then there's a system mode that can do things that are operating system like. And then you might have other modes that are above that manage other things. They may have greater access to hardware. They may have greater access to other parts of the system, or they may be patrolling parts of the system to make sure things have not gone wrong. Or there may be a hypervisor that's actually managing the different operating systems that live on the system. And those privileges usually come with different restrictions of what memory you can access, even what instructions you can use. And so that's what I'm talking about when I talk about privilege model. So in 32-bit, we've got many different modes here. We've got user mode, supervisor mode, that's where modules run. IRQs, when we get interrupts happen, they commonly drop down to supervisor mode. Fast IRQs that are meant to be unblockable and which will be used for devices that need to be serviced immediately. Abort and undefined that are used for when an instruction that is accesses memory that is not available, or which is an instruction that doesn't exist are invoked. Monitor, which I think is used for some additional operations, and system, which is kind of a cross between user and SVC. Chris has mentioned that FIQ was used for more than the floppy disk. Was FIQ used for more than the floppy disk and Ethernet? I believe on some systems it is. I don't know what FIQ is used for elsewhere. Modern things, I have no idea. It may be used for a whole bunch of other accesses, but it's hard to work with. It has a whole bunch of extra banked registers. And then finally, there's the hypervisor mode, which is intended for managing the operating system. It has more privileges and can do other things. It can also set up page tables of page tables and switch them out. I have never worked with it. Speak to Paolo if you want to have anybody who's actually played with this stuff. I had a look at some of his code and went, ooh, it's complicated. But that's how you might do hypervised switching operating systems on a 32-bit system. So the page tables, let's talk about what page tables are. Page tables are the way that you map from the memory address that you access yourself to the physical memory of the machine, which might have RAM behind it, or it might have memory mapped I/O data in it. Those page tables can be quite large and they have permissions that are set on them. So they can say, I'm allowed to access this in an unprivileged mode like user mode, or you are allowed to access it only in a privileged mode. Or it can say it's read-only in an unprivileged mode like user mode, or it can say it's read-only all the time. There's a couple of other permissions you can have, and in certain configurations of ARMS, you can also have different privileges based on the settings of different flags. You can set memory regions to all change in one go. It's quite confusing, but that's how that works. And then there are exceptions such as aborts, swipes, and interrupts that go through exception vectors. They dispatch out to the operating system so that it can handle those exceptions. In 64-bit, they've basically done away with all of that and switched to a system of EL, exception level. These are closer to how systems like x64 work, well, x32 as well. It's similar in some respects to the rings. I'm not going to go into the details of that because I absolutely don't understand how they are the same, similar or different, but they're closer. EL0 is basically where we execute things at, our user mode. EL1 is operating system. EL2 is, I believe, a monitor for the system, and EL3 is the hypervisor. Those two might be the other way round. I can't remember.
The other way around. Yes, EL2 is hypervisor. EL3 is supposed to be a layer
security
2.
monitor.
Yeah, so it's the security zone. Yeah.
Yeah, thank you. And one of them may not exist on some systems. So there we go. Yeah, I think Simon's just said that EL2 is for controlling 32-bit, he says. Yeah, definitely there's a bunch of things. You can have 32-bit at different levels, which is really confusing, but most of the time they're not supported. And you can have different page tables at each exception level. So these two, EL2 and 3, have their own page tables because they need to, because they're hypervisor and system monitor. And EL0 and 1, because that's operating system and user mode, they share page tables. There are some configurations you can change to make different things happen. And instead of the exceptions being based on what type of exception happens, the abort, SWI, or interrupt, the exception vector that's used is based on the privilege level that's invoked, which is actually quite useful, but it is a change in behavior. I'm not going to go into those too much, but basically, instead of knowing that you are entered for an abort, that the abort is stored in what's called an exception syndrome. It's a description of why we were entered. So abort, interrupt, system call, those are all set into a vector call, system register called exception syndrome. It's a weird name, but that's what it is. Okay, any other comments on privilege levels, privilege model? All good. Few, because this is an area that I'm a little bit rough on. Okay, so let's have a look at some actual code. So this is an example of how you might call OSINKEY. So a C call looking like that. This is the store pair of registers, X29, X30 being stored on the stack, decremented by 16, updated afterwards. The format is almost identical to an LDR STR instruction. For good reason, it is an LDR STR type instruction, just happens to store a pair of registers. And these are the X variant, so they're storing 64-bit values, so 16 bytes there. INKEY takes a delay and we want to convert it into an OSByte call. So we do a little bit of an operation here. We go and AND off the low byte here, and we store that in R1. We shift it down using the LSR instruction. That's like a MOV with LSR. LSR can have any sort of shift you like. And then we go and put a value into a register. Again, same pattern, same ordering of registers as we are used to on ARM. Bear in mind that not all instruction sets have this ordering of registers. Some use source and destination later. Here, this is a choice that I have made for my purposes. I am choosing to put the SWI number in X10 and then call SWI SVC 0. I'll explain more about that later when we come to some of the other parts, but that's what I'm going to do there. And this is what we're going to do. This is what the OSByte returns. So we do a comparison here with 27, exactly the same, and it sets the same flags as we do. So as it does on ARM32. So all of the branch operations that you're used to still exist, but they only exist on branch. So if that's equal, we can go and handle it with an escape, which is down here. We're not worrying about that. I'm just giving you a small snippet. If it was a 255, nothing read, then we do this magic instruction. Conditionally set inverted, because why not? So if the not equal state is true, then move that register into there. If the not equal state wasn't true, invert this register. This register is the 0 register, so it turns a 0 into a -1. And so we have a conditional instruction that did two different things all in one go, which is quite cute. It's a little bit weird to read, but then this instruction set is not intended for human consumption. It's designed more for a compiler. Okay. Then we pull things back off the stack. Again, similar style to what you would do with an LDR-STR pair. And the actual instruction to return is rect, which will move R30, X30, into the program counter. Any questions about the exciting instruction set that we can see here in the code? No questions. Way. All good then. Let's move on. So I'm now going to talk about what problems this causes. There will be more than I've got here, and I'm hoping that people will also point them out. So we'll move on to see them. Right. So these will be really obvious. For the instruction set, none of the existing software will work straight away. It's not supported in this instruction set. So it'll need to be rewritten, or it'll need to be executed through emulation, or by switching into 32-bit mode, 32-bit execution state, sorry, and then running things as before. But that state is going away, so it will need to be made to work. C code will need to be recompiled, and you'll probably need to modify it somewhat because of the larger instructions register sizes. But largely, it should just need to be recompiled if it's been written well. Most code will need some changes, though. Assembler is going to need rewriting. And we know there's a lot of assembler in RISC OS because nobody's been rewriting it in C, despite that it's been needed. Basic, which everybody seems to love, would need to be rewritten in order to make it work.
I should also point out at this point, Gerf, there's any amount of machine code, even trivial small amounts of machine code in God knows how many basic programs in applications.
That is a very good point. More so than there ever was in the basic that was in the BBC. So that is a very good point. Change of side, for example. It's a JIT. Yeah, so that's a very good point and one that I'd missed. Thank you. Yeah. But again, that's something that is a little bit specific and we can work with, I suppose. Norcroft won't work because it only builds 32-bit code. It would need changing. And why would you bother? Other compilers exist and they already build code.
I think I remember what I remember a while ago there was a thing on the there's a thing on the icon. There's a thing on the icon bar where ROUGOL was showing off a sneak peek of a very early version of an ARch64 version of Norcroft. I don't suppose you've heard much about it, have you?
No, I'm assuming it was an April Fool's type thing because there is no point in writing converting Norcroft to handle ARch64. It gives you very little benefit in the modern world, in my view. Their code was also wrong. It has a not invalid. If you tried executing it, it would not work because I can't remember the exact case, but I think they used the LDP instruction at the end in the same style as the STP, and so it wouldn't work properly. So I'm assuming it was faked. If it wasn't faked, then that's a bit of a waste of time, but yeah, fair enough. Maybe not a waste of time because it means at the very least they'll have used a disassembly code that was able to disassemble 64-bit, which is valuable. So maybe that's a good thing.
I mean, it's not like GCC for RISC OS is in particularly great shape at the moment.
That's fair. I mean, one of the advantages of just using a bog standard compiler is that it should just work. It will generate you valid code for 64-bit. If you follow that calling standard. The reason that GCC is not very good for RISC OS, well, two reasons, I guess. One is that it's having to use a different calling standard and conventions for certain things. And the other is that, well, our file system is a bit weird. That's going to be true probably into the future anyway. But those are the two things that are problems. Simon Wilcox has also just pointed out that GCC has many people working on it, which is nice. That's also true. And Clang and other compilers that exist.
If I can mention something, actually, I'm having so many troubles with GCC right now on RISC OS. It's also memory at allocation and deallocation. GCC loves malloc, but RISC OS it's a different story. So I'm literally crashing the compiler with code that is a bit more complex than a certain degree.
I mean, hopefully that would improve if you were able to do things with a not special compiler and more memory, obviously. Yeah. So next one is that some instructions that seem familiar don't work the same way. I mentioned the OR instruction that has a constant. That means that you can't OR constants that are certain values because they don't conform to its pattern. Have a look at the OR definition with a constant. It is kind of fun. It took me a little while to get my head around it, and I'm still not sure I understand it. There's also a fun instruction, ADRP, that gets the address of the page base. So you can give it an offset, and it'll go to the beginning of that page from where you are. And it assumes that the loaded code starts at a known page boundary, that's meant to say. And that's used a lot in the compiler. And the linker. So those make things a little bit more interesting for us. There's another problem with the instruction set, which I alluded to earlier, which is that SWI numbers that are defined in the in RISC OS are 24 bits because that's how big the instruction allowed for the constant. But in 64-bit, the SVC instruction, which is the equivalent, only allows 16 bits. So you only get SVC 0 through to 65535. Understandably, we cannot fit all of those RISC OS SWIs in there. So the decision that I made and you saw earlier was to have SVC 0 being RISC OS SWI and the value that you want, the SWI call that you want to use being in R10. This is not all that different to how other operating systems handle this case. If you look around, you'll find that a lot of them do similar things in their supervisor calls. Sorry, not supervisor calls, system calls.
Would you not take advantage of the fact that the OS SWIs are all small numbers and reserve the real SWI numbers for the OS calls and just use a register for module SWIs?
I was genuinely thinking of that, and then I thought, well, I don't want to put some special cases in there, and I'm being lazy. So at the moment, I haven't done that in the things I've been thinking about, but it's a really good idea to try and get some of those simpler SWIs in there. It would, however, mean that you'd have to go and extract the instruction that was being executed to go and find out the value. However, if you were to expect that actually 0 was important, you'd be doing that anyway. So I think it's definitely a thing to consider. It's not what I've done right here, but that's certainly a thing we could do with that, and it would give us a bit of efficiency.
Would it be? I think rest. I think this is. I think. I think the slice area from you propose is basically the exact same as OSCall, and there's basically the same thing as OSCall a SWI from standard RISC OS.
Yes, it is the same as that, and that's partly because of the caller SWI interface, and partly because the dispatch call internally uses X10 as well, R10 rather. So yeah, it is based on the same thing.
Well, I tell you what, if you're only going to use one number, then please use 6F rather than 0.
That's a possibility. I don't really mind which one to use, but I suspect that there will actually be 2 that would be used, and I'll come to that in a little while.
SWI X12.
Right. So one of the questions, the comments from Simon was perhaps we should use a number other that isn't used by other systems. Linux went and used OS C. Yeah, that actually might be a nice idea. We might want to do that. Yeah. Simon's also suggested there's a register that tells you what SWI number is, the SVC number. That actually is quite useful, and I hadn't seen that. I thought it existed, but I couldn't find it when I looked. Sometimes the ARM documentation is a little obscure. I may be understating that a bit because I find myself swearing because the page I previously found I've lost and I can't find things. So that would be really good. Right. Somebody else asked a question about how do you define what is the OS when most things are modules? That's a reasonable question. Basically, anything that you load as a module is a part of the OS, but I'm not going to get into the philosophy of what you think RISC OS might be, because I think we could be here quite a while. Maybe that's something for next week. Actually, what do you think of as RISC OS is actually a very interesting question, but not one that I'm going to get into here because I think we would all argue for different things. Any other comments on? Hang on, I guess we could use.
A key point is that any RISC OS module is both operating system and application and command line, amongst other things.
Yeah, it's a bit of a mess when you think about separating functionality.
It's glorious.
Yeah, so that's an interesting one. Chris has suggested you could use the SWI number itself, like we use SWI bases, so we could actually have the SWI base mapped into the SWI SVC number.
16-bit is too small. No, I mean I've written more than 400 modules myself, so no.
16 bits is 65536. So you could use the. Anyway, sorry. That's an idea. I don't know that it would work, but that's an idea. Let us move on, though. Oh, hang on. Given that 64 will break everything, should modules still be a thing for applications? Well, that's a question that again moves into what is RISC OS. I think if you feel that system calls and extensibility and the like, and being able to bring those things together is RISC OS, then yes. But maybe it is a good question to ask. Maybe it is something that we should think of differently. Modules are basically 6502 BBC Basic, BBC ROMs.
Sideways ROMs, yeah. But
yes.
the key question is basic. Do you expect to have a basic interpreter? In which case, the basic interpreter is an application.
There's no reason for it not to be an application, or it doesn't need to be a module. It never did, but it just happened to be.
Shared code.
Shared code, yeah, but I mean that's something that we could do in other ways as well. Again, there are different approaches rather than the way that things have been, and the further you deviate from what RISC OS currently does, the less like RISC OS it is, and the more likely you are to get something that breaks. And that's something that we all recognise, and we all have to balance that in different ways. I don't have any answers for that, and there are lots of different ways of doing things that could make things easier or harder. Okay, shall I move on? Okay, memory. So larger memory means that pointers are larger. So instead of being 4 bytes, they're going to be 8 bytes long, or still a register, obviously, but the register is larger. Any API that we've currently got that uses descriptors in memory will have to have something changed about them. Registrations that use pointers and descriptor blocks, anything in the WIMP will have indirected text pointers. They'd need to be 8 bytes rather than 4 bytes. That changes a whole load of behavior. So that's something that it causes a problem for. Any questions on memory? Problems that are caused by the memory size being larger? Because that's all I've got to say.
Given that ILP32 was mentioned earlier on in the chat, would it be how plausible it would be to you? How plausible would it be to use that? How plausible would it be to use? How plausible would that be? Was it to be to use that for AR64 up front and then switch to 64-bit pointers later?
You've been reading the end of my slides, haven't you? Yes, that is one thing that I will propose, but you're jumping the gun here. Yeah, that is one thing that because it keeps all the APIs exactly the same, and we can move without breaking quite as much of the world. I will come to that in a moment, but yes, that is what I'm. And again, you might disagree with me on that. There's a whole bunch of things that can be done differently. So, registers. So actually the registers themselves don't give us much problems. The larger number means that things are a little bit different, but not that much. The environment changes because the exception registers are moved, but that's about it. You end up with a exception size that is something like 140 bytes or something. Bigger than that. Oh, I can't remember. I mention it later on. And the stack being 16-byte aligned means that handwritten code, you need to be more careful. Otherwise, things go bang. But you shouldn't be writing handwritten code most of the time unless you're actually implementing libraries and stuff to access system calls. Or you need something really fast. There are reasons, obviously. I don't think the registers themselves causes any other problems. Does anybody else know any issues that are caused by just the registers being wider? No? Okay, cool. It's good because I didn't think of anything there. Okay, so the calling standard. Simon's mentioned that C things go bang today if you don't have stack 8-byte aligned. I haven't ever been in a situation where I've seen that, but that's interesting. I didn't know that. That's on 32-bit ARM, Simon. I'm assuming so.
It's certainly true of WinCE for ARM. That had 8-byte stack alignment.
Oh, right.
Yeah, it was the calling standard. I got hit with it. I was starting tasks that ran some C programs, and you could give them any stack pointer you wanted. And some of the time they were 8-bit aligned, sometimes they were only 4-bit byte aligned, and then they broke.
Interesting. I will have to pay more attention to my code, which is almost certainly breaking that convention. Okay, so my first point here is that we've got no static base. There's no equivalent to R9 reentrant code. And that makes certain things difficult. If you're not sure what that is, then that is it's a slightly different problem, but it's something that we would rely on for module code if we were to have different module workspaces. So that's one thing. We don't encourage the stacking of registers. So the registers that we usually get out in the backtraces wouldn't appear because they're not being stacked by default. It's not required. I mean, it's never required in APCS, but we do it. So you lose a little bit of information from the backtrace. Now that can be helped by having debug information. So there's a little bit of help there, but that's something that's interesting. Similarly, all of the modern compilers don't write the function signature strings before functions. So that also affects your stack backtrace if you use the same convention. Other systems get around this by having a symbol table and producing relative values from that. Fair enough. There is no stack limit register. So software stack limiting is not encouraged and is not supported by any of the compilers, at least not that I've seen. That also implies that chunk stacks are not supported. I mean, they could be. You can do anything you like with the calling standard. But if you want to be compliant with the rest of the world, That's something that's different. They basically assume that you will abort when you hit the end of your stack. So that's a little different. And without a static base, having modules that can be instantiated is harder, because we don't have some register that can go and produce us a different base point where your workspace is stored. Anybody else want to make comments on the calling standard and the problems that it causes?
Well,
Yeah.
only that different operating systems have different calling standards, and that's always been the case.
That's always been the case. Most of the systems do follow the same style of things from ARM. They don't tend to deviate too far from this, and that's because that's what the C compilers generate. You can vary what Clang and GCC produce, and they're obviously custom compilers, but that's the basic things there. And I'm strongly in favor of just use the standard compilers, because they've had lots of eyes on them. They've had lots of development. They're very efficient these days. You can still write better assembler, but you have to try hard because they're pretty good. Okay, move on to the privilege model. So I've only made one note about this because I couldn't think of any other things. You can't check what exception level you're currently in EL0. That's an undefined instruction. So the way you find out whether you're in EL0 is whether checking what mode you're in gives you an undefined instruction. That's not very nice. Okay. Peter said, other than the current RISC OS API, the SWIs, we don't follow the current calling standard at all. It's random register usage depending on the system call. Yeah, that's pretty true. There's also the fact that whatever you do in your application in RISC OS is whatever you like. We don't actually have, although APTS does define that we can use things this way in the calling standard, you can write anything you like. That's less likely to be true, particularly if you want it to work with other code. And I suggest that we do. We want to make as much reuse of code as possible.
Should we be checking to see if we're in user mode or not? Shouldn't we know already?
So consider you're running a module that is also a task. If you're trying to have a module that is also a task, you can check what mode you're in and decide whether you're executing as part of your task code or your module code. Most of the time, you wouldn't need to do that. But say if you're trying to implement malloc and you want malloc in the module side to go to RMA, and you want malloc in the application side to go to the application space, you need to know which one you're in. And if you can't, that's more difficult. So that's really the case that I encountered this in, or encountered it as I'm designing stuff anyway. Give me a second. Right. So that is the only case, though, that I could find with the privilege model being different. I mean, obviously, the completely different privilege model, exception level model, means there's operating system issues, but that's just not something that you're not expecting.
Was that a hint?
It wasn't a hint to get a cup of tea, but thank you. Okay. I'm getting a cup of tea. So let's move on to RISC OS APIs. What the problems RISC OS APIs cause. So I'm gonna get on my little hobby horse and say enteros and intof, inton, leavos, they're just bad. You shouldn't be jumping in and out of different privilege levels. You should, if you're in user mode, you should stay in user mode, and you should go through in and out of things only as part of system calls, not jumping in and out of them. It was a bad design, and try and fix that for 64-bit. Don't even allow it. I mean, you'll still be able to get into user mode because you can set a callback or something, but I think that's a largely a moot point because you've got the choice to go and redesign these things. Other APIs use flags for input and output. It's a bit awkward. So read escape state, read C, read line. They return the escape state in C. bget and bput returned that there was an error in the C flag.
I mean, it's worse than that, Gurf.
Oh, I know. There's
Don't
loads of them.
forget, as RISC-OS Open forgot, the caller vector takes the V flag as a parameter on entry.
That's fun. I mean, it's not like we've got anything there that is particularly weird. We just need to try and make these things more standard in the new system. And I suggest that even signaling as a V flag is pretty unfriendly. So maybe we limit its use. Maybe we don't. Maybe that's the right thing to do. I'm not sure. In this case, I think getting rid of the C flag and the V flag for caller vector because of insert V, CNPV. I think I mentioned it on the next page. No, I don't.
Yeah, there are a few vectors that do it, and it's even more complicated than that. And now is not the time. But what I would point out is that when I wrote as part of the Nucleus project, when I wrote the OS32 module that implemented a 32-bit API for things like OsHeap sort that used to take flags in address fields. I encoded the flags into the SWI number. Ooh. So there were actually 16 different, well, there was something like 20 different versions of OS32 heap sort. But there were 16 of them with the 4 flags hardwired into the SWI number. So if you knew from a programming point of view which flags you wanted to use, then there wasn't an issue because you didn't have to squeeze the flags into a register. It's only when the flags are being decided programmatically that they needed to be in a register or in flags, etc., etc. So there's no reason why caller vector couldn't exist in 4 different versions.
Possibly. I mean, I think the best thing is just to redesign them because you're not going to be calling them that often, and just make them so read escape state, maybe return R0 as the state. Just do it. Make read C return R1 as having an error flag or something. You're not going to be calling those calls very often because you're going to go through interfaces. That's what I would reckon. But we have the opportunity to go and redesign those and avoid using flags, is what I'm saying.
Much of this nasty low-level stuff is only going to relate to OS-level code anyway, not user code, really.
Yeah, I'm really hoping that this is abstracted away by library code because we'll be writing in C or some other language. I'm using C as the example because C allows us to port things that have already been written very easily. But other languages like Rust would do really well, though not allow us to port quite so much. It can interwork though, which is what you want. Anyway, that was parts of that. The next bit is about executables. So executables need to be runnable, they need to be recognized and safe to run on older systems. You'll remember the AIF header changes that were needed for 32-bit, module changes that were needed for 32-bit, utilities as well. And there'll be some APIs that need to change to actually reflect that this is a new architecture. And so if I'm thinking of things like the OS re-platform features, I think it's called. Or is it just OS platform features? Can't remember. Which makes very little sense for the existing calls to even be used on a 64-bit system because the things that they encode probably don't even exist. So some things will be different, but mostly, as Nemo says, low level. So let's move on to the other. Oh, and sorry, is there any other RISC-OS APIs that people want to bring up? I mean, there's lots. So
yes, the answer to that is if you start bringing them up, we're going to be here all night.
Yeah. I realize I'm taking quite a while on this, and we are only on slide 25. I'll try and talk faster. So, other problems. Most applications won't exist for RISC-OS.
What does that mean?
It means that you can't run your regular applications. You're not going to be able to run Sibelius.
Then that's not an operating system. That's
yes,
a vase. It's a decorative vase.
No, everything you start writing is a system that doesn't have anything else. That's
yes, but this is a 40-year-old operating system, so you need to be able to run all the existing software.
So write things that go and provide the lower level system. As I said, the emulation and the provision of 32-bit support layers is not my concern in this talk. That can be a discussion for another time, because just getting the operating system to 64-bit is what I'm talking about here. So, user base is small, the developer base is small. Those are also quite restrictive. And anything for 64-bit may take away from RISC OS development, so you won't have things going elsewhere. That's fine. That's for people to decide, but they are problems that exist. As Nemo says, there are issues with running other applications as well. That is one of the things I'm mentioning, but that can be addressed in other ways. You have to deal with those. So, how can we address these issues? Okay, so first thing is we have to decide what matters, and RISC OS is very complicated. We'll have to decide what's important for now and what's for the future. And we have to do something better than just talking about the problem for another 20 years, because really people have not been addressing this issue. A lot of work could have been done, yet people can insist on writing more assembler modules. They insist on extending the modules rather than rewriting them in C. You need to do something about that and make sure that the system is actually updated so you can actually run it if you want a new system. If you don't, then that's fine, but that's about moving forwards. It makes sense to do things in a piecemeal way so that you can get the small parts of the problem addressed at a time, and we move forwards. Things like rewriting small modules as you go. Julie Stamp has rewritten the obey module. It's one module, but nobody else has done that. It's a big deal. People should be embracing the fact that somebody has converted an assembler-only, a quite complicated assembler-only module to C. Why is there no message trans? Why has color trans not been rewritten? Why have any of the others not been rewritten?
Let's not talk about color trans.
It's a module like anything else. It has system calls. It's relied on by a lot of the system. Why has it not been rewritten? I don't think that's a sort of source of derision, other than the amusement at the fact that the system has not been addressed. These things could be, but they haven't been. So we have to decide which of these things matter. And we need to make the steps in the right direction for ARC64. Thank you very much. Wonderful. I've lost where I am now. I'm easily distracted by its table. So we need to make pragmatic steps to move in the right direction, even if it's not directly from ARC64, like just converting things to C. Convert them to C and check that they work. And then your life, when it becomes 64-bit, will be simpler. It is important to recognize that this will take a long time. It's not a do things overnight. It's not a do things for the next year. It's going to take time. You do things in small ways and you can see that there will be progress. And much of this won't have any user visible end effect. You won't see users going, oh, wow, look, there's a new version of message trans. It's exactly the same as before. Okay, that's exciting. That's just the way it goes. On the other hand, they may be more efficient. They may be more maintainable. It may increase your velocity in actually trying to add new features where you need to, because adding new things in a high-level language is way easier than adding it to assembler. If the file core had been converted to C, maybe we'd actually have a modern system that was actually more sane and able to be worked on. Maybe, maybe not, but it's file core after all. I've talked about many different aspects of the problems, and there will be many things that I and other people have considered for these, and I may be different. I've only got experience with what I've done, but I have written an entire version of RISC OS, near entire. So I have a different outlook, quite unique to other people. So I'm going to go and talk through some of the areas and how I feel they should be handled. These are my views. They're not anybody else's views. I have looked at how some other people have talked about this, but they're my things. So, firstly, the instruction set. It's only a problem if you're writing lots of assembler code. And we should stop writing assembler code like 20 years ago. Stop it. Don't do that. Everything in C no assembler or just tiny amounts. Out of line with your primary source, not inside your C code, because then you're tying it to the particular architecture. User interface libraries can easily be replaced if the interface changes. Just change your library so it does something different, and your business code can do things the same way. And assume that your C compiler or similar will be ARC64 rather than handwritten assembler. It makes a big deal. Next. Since the SWI cannot fit into the SVC instruction, use a register. I've talked about that. And again, call a SWI, as Cameron mentioned, was the thing. Or was it Nemo? Can't remember. Whoever it was, yeah. And I've defined here that the SVC calls will be SVC0. Yeah, could be anything. In Pyromaniac, I've defined that SWI numbers FF00 are actually special because they're internal. Many of the interfaces will need to change if you want to use the whole of 64-bit memory. All the control blocks that I talked about, the descriptors will be broken. Or you'll need to create new APIs to do things. We'll have OS readline 64 and things like that. So initially, just don't support the full address space. Just use 32-bit logical address space. And then all the APIs have a one-to-one mapping. That makes it a lot easier for you to move between the old system and the new one. All the APIs are the same, just a few oddities like changing the way that flags are handled or things specific to the structures. Make those different. Use the SWI number for future expansion. So maybe 0 means compatible with 32-bit, maybe 1 means compatible with 64-bit. And we can have special codes for that. Maybe. I don't know, but that's one way we could do that. We could handle those. That actually goes against what Nemo said about using the low numbers, and I actually really like that idea. So, don't know. But that's one thing you could do, and I'm just defining 0. I also like the idea that somebody suggested, I forget who, that we use a different number than what the rest of the systems use, so we could actually...
Just a quickie, I don't want to interrupt and make a big discussion about every point, but... if you've got a 16-bit sort of physical SWI number, presumably you're still going to advocate that one of those bits is the X bit.
I wasn't actually. I was going to leave it in the SWI number, but that's an interesting idea. I hadn't thought of that.
Well, no. What I mean is, if you thought if you were going to say do the low numbers as OS SWI numbers, then you do need to have an X in there.
Yeah, you do.
But you could take the opportunity to also have a 64-bit bit.
I like that. That's a really good idea. Yeah, thank you. I like having the idea, having people throw ideas at me because things I haven't thought of. I've thought a lot about these things, and I'm going to be blinkered for some. So thank you. And again, this also fits with we have the option to decide how we do this. I'm not going to say the right things, just how I'm thinking about it. And I'm trying to go faster because I know we're running out of time. So x18 was defined for operating system use, and it isn't used the same way on all operating systems. I don't know what to use it for. In some cases, it's used for thread context. I had considered using it to mean EL0 is x18 is set to 0 when in user mode, and that allows me to check whether I'm in user mode or not. But I don't think that's a good idea. Wasting an entire register for your mode.
Well, it could be your base register for modules and 0 for user code.
It could be. I mean, that actually might be a thing, but then nothing would know how to use it. There are options with that, which, again, could be quite handy. Calling standard. This is one thing that I said earlier. Adopt AAPCS as the only register mapping on the system. You stick to that for pretty much everything. And then backtraces become natural, and you can start interpreting things and assuming interworking more easily. If I'm wanting to write everything in C anyway, this is natural, or Rust, because it will follow the same calling standard. SWIs can be passed in registers, X0 to X9, same as what we've got currently, and the SWI number in X10. I talked about that. And to return as well in X0 to X9. That's a little bit against things, but yeah, that's just the way I thought it might work. I'm not sure about that completely. And assume that you'll always have floating point. if you sorry, not floating point there. Sorry, I've read that wrong. That's frame pointer. The frame pointer is always used. You always trace the execution. I did have something else previously about floating pointer, so I forgot. I've deleted it. So SWISE will look like this. That's what we talked about before. And if you put it in a function, it looks like that with the store a pair of registers, read C, return. And because it's gone in with coming out with R0, you've got the same calling convention there. Nice and easy. Because there's no static base, module instantiation is harder. So let's not try. Just get rid of multiple instantiation of modules. It's just not used well, and FileCore uses it. It almost certainly shouldn't. Preferred instances are a pain in the behind when you're trying to use SWISE and star commands. And anybody else who understands preferred instances and has used them usefully will know that they just screw you up. I implemented the AM player system, so yeah, that was a bad idea. AM player using preferred instances to switch around, no. It's a bad way of doing it, and modules can be designed better. And it simplifies things. I've mentioned that user mode applications should remain user mode only. That's something that we should try and stick to. It would be really nice if we could define privileges for modules as well. I'm not quite sure how, but it might be something that we could have a look at because we have the option to do something like that. Maybe. Something to think on, because there are options available when you're redesigning these things. The external APIs. So I'm going to talk about a number of the APIs now.
Can I just to make a comment about privilege levels? One of the big problems in RISC OS from a security point of view is that there are no privilege levels in the API. And a very good example is memory allocation in the RMA, which is ubiquitous for user mode applications and also for filing system and operating system core functionality. And that there's no distinction in the API between the two, and there really ought to have been.
I think you're quite right. And I think that's something that we can start to address by replacing parts of the RMA calls with other things and not needing them to be used, I think would be a good thing as well. So that's what I'm thinking. I don't know whether that's actually possible, but people could experiment with that and see what happens.
And new reason codes, really. That's all that's needed. Yeah. I've got two RMAs on my system. I've got a high RMA and a low with different reason codes. So there's no reason why you couldn't have a kind of user mode RMA, module RMA, super high security RMA with fence posting and huge gaps between allocations, etc.
Yeah, I'm in favor of that sort of thing. So external APIs, I would say start ensuring that we have tests for RISC OS APIs so we can define what they do and we can compare them to the new version that we're implementing in 64 bits.
You'd have to work out what the existing ones were supposed to be doing first.
So you write the tests to prove it, and then you know, and then you duplicate. You duplicate by your tests. It's the definition of handling legacy code. And as you'll know, I'm a big proponent of that for this sort of reason. And because RISC OS Pyromaniac needed to guarantee that its behavior wasn't changing and that it matched closely enough the standard behavior. Write your tests, do it in everything. Characterizing the behavior means we can replicate it and the implementation, or we can decide that we want to have a difference in behavior. We can identify what the behavior was and that we are going to do it differently this time. That's more important, more useful than just going, it's good enough. I don't like doing that personally. And you're going to break things. At least you're going to break things without realizing. And as you implement stuff, you can be warned that you've deviated from other people's expectations or your own expectations. So next, redesign the flags to avoid APIs to avoid flags. I've already mentioned that as a big thing. This is where I mentioned CNPV. Just shoot it. It's a horrible API. Maybe not shoot the vector, but just replace its input API.
Reason codes.
Yeah, that would be a perfect way to do it, yes. Yeah. Why it's done that way is purely 6502 basic.
BBC Micro,
BBC Micro, yeah. Environment handlers. Environment handlers should never be entered in EL1 in system mode. They should only be entered in EL0. That's closer to how applications work in other systems. And trying to do that similar way may make life easier. And I'm very much in favour of that. Have been for years.
Presumably, you're not including the exception handlers there, though,
I'm
because
not
exceptions can happen anywhere.
So I'm including exception handlers in the sense of, oops, gone too far. In the sense of change environment data abort and prefetch abort should not be handled by the. It should be handled differently. So you should be entered in EL0. The processor vector exception handlers should still be entered in EL1 in the supervisor mode. That's what I believe is the way to do it. If you're handling the processor vector, you're handling it at a higher level. If you're handling a change environment, you're handling it at a user mode level, and you shouldn't be able to privilege escalate in that way. And there is no reason to. There just isn't a reason to. If modules are written in C, make them easier to work with. So instead of having the calling convention for modules be as thin as it is right now, actually make the operating system put the values into a block and pass the block in. Just reduce the CMHG veneer down to almost nothing. And that can really simplify things. It means all your modules aren't duplicating the same chunk of veneer code. Why even have a veneer? Why not actually have C functions that can be called as part of your module? That makes things easier.
The reason for the veneer is that the calling standard used by the compilers is at complete odds from the calling standard defined by the operating system.
Yeah, so make the operating system. Yeah, so in my definition I've set up, I still use R12, but it isn't useful because R12 doesn't make much sense if you haven't got a module instantiation. You can look into that in different ways, but that's the way I'm thinking about it. Just simplify the whole process. Same goes for commands. Commands can pass in the parameters in R0, R1, R2 in the same style as they do for the command entry veneer in CMHG. As I say, just make it a C function, no veneer at all. That may not be possible, but the closer you can get, the more naked you can make your module, and easier to test. AF files, executables. Absolutes have already got a way of recognizing that they're not compatible by using the header flags. Now, they're not supported by the older system, but you could use Service UK compression to handle that. We can update the header to define it as incompatible with 32-bit systems if it's run easily enough. If it is run is easy enough. Yeah, that's right. And we can define the initial section of the AF to be 32-bit ARM with headers set. So here we go. This is what I have defined as being a RISC OS executable for ARC64. There is no special cases in here. We've just got some extra values that are the same places as they would have been, read-only size, read-write size. 0 init size are the same. And if it's executed on a 32-bit system, it will go and print out the message as an error. ARC64 binaries cannot be run on 32-bit RISC OS, because they can't. That is relatively simple. The main thing is that we've got a 64 in the address mode, and we can again include some flags in there if we want. And then the 64-bit code starts at offset 100, just to make it easy for us. And it can have relocation code. In my case, I'm not currently using it. Some zero initialization code, and then a start entry point. And again, we'll have an exit in the end just in case you return. I've removed the decompression entry because it's not actually worthwhile having decompression. Why compress things when other systems exist and memory's cheap, disks are cheap? You can distribute things using zip or other formats more efficiently. Having things compressed makes patching harder, and just why bother? What are you gaining from that other than the fact that your file is slightly smaller, which, as I say, memory and disks are cheap and they're fast these days. That's my view. Disagree if you like, but yeah. And in the future, only use ELF. That would make a big deal out of this. It would make things a lot easier. If the operating system supported it, why not? In fact, we'd even do that earlier on. but you still have to implement it. It's not something I've done right now. Modules have a standard feature flag that differentiates them, and I've already started using these. I've defined the feature flag with bits 4 to 7, containing 0 for 32-bit, 1 for 64-bit, 2 for x64, 3 also means thumb, and then 15 means Python. This is all defined and documented, and you can find that elsewhere. I am trying to rush. Please forgive me. I realize it's just getting late. I'm trying not to overrun too much. But this setting of the feature flags won't work on earlier systems because they don't understand the feature flags. But if we set bit 30 of the module initialization, then we can cause those older systems to fault those modules. And this can indicate that the architecture is present and that it's not ARM. That will prevent them from loading, and we could even recognize it using service module pre-init on those earlier systems and produce a better error message. We can also include a zero initialization as well to say that this module needs 0 in its space, which could be useful. It is useful. The OS can then reserve you some space for that. And this is what it would look like in GNU Assembler. So this is the layout of the module. It's very similar to what you might normally expect. Offset to some code, extra bit being set here. All these values are still 32-bit wide because you're not going to have modules that are 4 gigabytes long. You're not, really, you're not. And the module flags have an extra bit here saying, this says I've got 0 initialization space present, and this bit means I'm ARC64. And again, you have the module headers and help message the same way. And then you've got the code at those points being ARC64 code. Because the compiled code uses ADRP to get the relative address of the start of a page, it makes things a little bit more difficult for modules, because modules traditionally are loaded from at an address with offset 4. But if the modules expect to be loaded at a page offset, then that's going to be a problem. So I recommend that we actually make the modules loaded at a page boundary.
There's many things that expect to be able to read the length of the module from the word before the start of the module.
Yep. So I recommend that it actually starts at the page boundary plus 4.
Plus 4. Yes.
And that is an invisible byte that is defined there. You can use linker scripts to make that happen. Yes, but for that very reason, you don't want to be. It may be a bad idea, but it also means that you can't corrupt the length of the module if that page was protected as well, because code should be protected. An additional thing, we could, in 64-bit, modules can be in a managed area that loads at that page boundary plus 4. That can be a special form of OS heap. In RISC OS 5, there's already a load at particular alignment, so that should be possible. Traditionally, modules were loaded into the RMA, relocatable module area. Since there's different requirements for the code and data, why not place them in an explicit module area, which has this form of heap, and then change the RMA to be random memory area? Because as Nemo says, that's exactly what it's used for. I've defined dynamic area for modules to be number 9, because that's what it was reserved for in RISC OS 4. There's also protection that could be done in there as well. I've not done that here, but it could certainly be done.
Can't modules use have their own application memory area?
They can, and that is fine. They could access that. How that exactly would work, I'm not currently sure, but you don't tend to have code being executed in those areas. So that's a thing that would need to be dealt with. Modules could even be defined to be something different in the future.
The basic interpreter is an example of a module that has the application space and executes code in the application space.
Yeah, but it doesn't execute most of its own code. It just copies chunks in there, and it probably shouldn't.
No, what I mean is the basic program can assemble some machine code and the basic interpreter will call it.
Yeah, that also is something that we'd have to support. may have to support, sorry. There's different ways to handle that.
but that memory is protected from other people messing with it because it's in the application.
So you want to keep basically the real assembler in the BBC Basic Interpreter?
I don't want there to be a BBC Basic assembler that's actually got the assembler in at all. But sorry, are you talking about the assemblers in the square brackets assembler?
Yeah, so the assembler
Oh.
in BBC Basic Interpreter, yeah.
I think that there's no reason why you couldn't do that. It's just another language feature. I don't see why you wouldn't. I mean, it'd be nice if the particular variant of assembly that it could produce was different, so you could actually say, I want to use
my
different.
version of that is how my version of BASIC works.
Yeah,
Yes.
and I know that other people have produced different patches to regular BASIC that let you build 6809 and 6502 code in the RISC OS BBC Basic. Why not do that all the time? But that's a language feature that can be done entirely separately. It's yeah, go for it. I really like that idea. I want you to build x64 code in my BBC Basic.
Yes, it should be completely straightforward. It uses a protocol called BAD, Basic Assembler Dialects, and my first prototype was called Bad Basic. So there we go, whether it's a good idea or not. I haven't done it yet, but I want to build an AASM compatible that uses the same protocol, if you see what I mean.
Yeah.
So you can reuse assemblers across both anyway.
I mean, those are tools that would be really useful because you'd be able to build those things on the main system and make them go across. It would be really quite nice to build things on 32-bit systems that could be executed on 64-bit systems or others.
Yes, and the other nice thing about Basic Assembler Dialects is you can switch dialect from line to line at any point. And so if you're building, for example, your module that has 32-bit ARM code and 64-bit ARM code in it, then it's trivial to switch between the architectures.
That would have been quite useful for some of those things I've written. So let's move on to utilities. They've got a standard header that's been defined. It just hasn't been enforced in any way. That could be. And we can reuse that form in the same way as AAF files. So instead of just saying it's 26-bit or 32-bit, let's build it as ARC64. And it looks kind of like this. So you've got your start entry point that jumps to the ARM32 error message. Again, same error message. And some markers that reuse the same data. And here is your ARC64 entry point offset. Similar sort of thing as AAF, and that can be recognized really easily. It's a very simple entry point that keeps those utility files safe. So, architectural APIs. The decision to use 32 bits of logical space means we don't have to design any of the APIs. We can keep all our pointers down at 32 bits. We can do a whole bunch of things that will just work when you recompile them. And the bulk of the APIs won't change. So if you do port a basic, then most of your basic that calls SWI calls will just work, excepting those flags, obviously. And you can later enable some larger memory regions. It also means that you can reduce the problem to one of language. The instruction set needs to be addressed, not the mechanism by which the operating system functions. And by keeping yourself in that area, you have a transition system. I mean, it might be that it actually sticks in just using 32 bits for a very long time because it takes a long time, but it could be done. And you'd still have chips that could execute it. The debugger module, it's already got a disassembly for ARM, but it's actually disassembling the instruction set used by the current system. And it will need to disassemble ARC64. I've also provided a disassemble ARC, which allows other architectures to be disassembled. That supports ARC64 and 32, as well as Thumb. And we can disassemble ARC64 code in the Pyromaniac system. If you want to go to shell.riscos online, you can disassemble things in ARC64 already. I've also been re-implementing the debugger module, as you may know, on my live coding, and that will be able to support that as well when I get to it. Sorry, I'm spinning through this quickly. Please tell me to slow down if it's getting confusing. So, to make it easier to understand the architecture we run on, we need to be able to do some introspection, to be able to ask what the system is. I've created OS platform features 64 to describe the register layout used by the exception block. That allows us to know programmatically how the block is laid out and what the registers are called. That means that the implementation of the debugger becomes a lot easier. You just read the block and print out the data in the block. That's it. And that's already implemented in my new debugger and in Pyromaniac for that matter. The size of the buffer in Pyromaniac is currently 33 64-bit registers and one 32-bit register for the P state. And that's the size of the environment dumps. You can find this documented in the Program Environment Supplement on the Pyromaniac site as well. These slides will be available, so you'll be able to find the links. Some informational interfaces will need to change. So OSByte 81 returns a something for the architecture stuff. Maybe we should return hex 40, which is 64, because that's actually a free number. Some of the platform features don't make sense. Platform class should probably change. But in most cases, the user-facing APIs are going to be exactly the same. And that makes things a lot easier for just keeping things working. So what about libraries? The C library is obviously vital to the system and you need to have one. So we can implement one, or we can just use Codemist's one that's used in the shared C library. Other libraries exist, Muscle, GNU library, other libraries for BSD, so on. They all exist, but you can write your own. There's always RISC OS lib, and that's used by a lot of things, so it can probably be converted as well. Again, just recompile it with the right sizes of structures. OSLib has got defmod that produces assembler files. All it needs to do is just write out assembler files that are 64-bit, and I've got my own parser that can read them and could be made to run and generate ARC64. I've started doing that. It doesn't work, and that's where I discovered the OR problem. That particular instruction doesn't do what you think it does. C modules and applications. We should just convert them to modern C, recompile them, use some tests for the original code or write them, and then run them as they stand, because they should just work. You can always get extra tests for things. I've included a number of tests for different modules in the repository, and I've got more in Pyromaniac anyway, so people can use those if they want, or they can write their own. Nemo's just suggested from the early one, there's a lot of code that will compare that whether it's greater than a particular version. So 40 might not be bad, would be bad, sorry. And yes, I know it's not limited to bytes. That is a very good point. Why not do that? It might confuse other systems, but that's not a bad idea. Yeah, I like that idea. That's another good one. Assembler-only modules. I know what I've said before. You know what I've said before. Rewrite them. Get them into C. Start from the documented API. Don't try converting the assembler implementations unless you really require to. It's just painful. And I know that it works by just working from the documented API because I've done it for a good chunk of RISC OS already. And trying to perpetuate that insanity by creating assembler modules from scratch, no. Write the tests, compare the assembler in C, and see how it works. And you can even do that on the standard RISC OS 32-bit because that's what it's for. And you can release versions as soon as you have them available, and people can try them out and see where things break. It's not unlike the way that the Internet module was handled. The Internet module was released and people tried them out and saw what applications broke. And things break. And of course, you've got another expert in the field, Julie, who can give you some good advice on what's difficult there, hopefully. I'm volunteering Julie, I'm sorry. I'm very impressed with her Obey module. So let's have a look at some 64-bit code. And we are now at 9:30, and I realize I'm running really late, and this is probably going to be a bit of a pain for people, but some utility code. So this is utility code. It takes the message to set to print in R1 and it prints out hello world or hello whatever your name is. And it's not very difficult. I've retained the behavior of write S, and I have no idea whether that's the same thing. I don't think write S is a particularly useful SWI to keep. And then we're going to read in parts of the message and do a conditional select like you saw before, print out the message and call new line. And then finally, we'll return that there's no error. Rather than setting the V flag, we just return it with 0. And that becomes your error pointer. That's what I'm suggesting for utilities. So we can run this code with a couple of commands. So let's try doing that. I'm going to try running it with both plain, and then I'm going to put some tracing on. So let us see if we can do that. I need to change my sharing. Give me a moment. And if I can find the right window, terminal, here we go, share. Right, has that transitioned to the terminal window? Yes, good, all right.
Yes.
So here we go, pyro, oops, click in the window, pyro dev, nice command. Oh, I've forgotten what the command was. Hello world. It's really sensible. So here we go. Run hello world. Right. Very exciting. It printed out hello world. Let's turn on the debug. Tracing. And there we go. We have now executed that code, 64-bit ARC64 code. And the trace has shown us what the registers were each time, showing us that we executed a write S. We've got a pointer to world. We've got some conditionals here that have got particular pointers in them. And then we've written out the world, and then finally the new line. There we go. Very simple. And that was the utility. We can actually have a look at what that utility contains by doing a dump I on hello world. Oops. Quotes around that. So if we just have a look at that, we can see that this is, here's our header, that is the code that's there. Then this is the code that would be executed in 32-bit and the error message. And this is where we actually enter the code, which is this 5C offset here. And then that's the actual code that's in there. It's all very simple, nothing particularly complicated. There we go. So that's a simple utility being executed. So let's return back to the slides. Back to the slides, which I forgot to move on. That was our demo. So next thing, C. This was just to show that you can write them and what the code looks like, but we're going to be writing C code most of the time. So let's have a look at a C Hello World program. This program does a little bit more than the utility. It's not particularly complicated again, but here we are. So this is the sort of code that I've got. Hello World printf, studio, printf hello world. If we got some arguments, print them out, and then print out the C library version. C library version is the Codemist library, standard C library version string. And so now let's do a demo. Do a demo. Where's it gone? I've lost my window. This one here. Share. Right. So c.absolutes. Okay, and then we'll run the commands in there. Hang on a second. I've forgotten what my commands are. Pyro dev and hello world printf. Whee! So we'll run that now. And as you can see, it runs and it's printed out our message. It's printed out this C library 64, and we've got Jerf core because core was actually the label that was used there, and a version string as well. That's my C library that I've written. and you can see what it's doing there. We can have a look at what that code is. So we can actually, yeah, go on.
Question. What
Yes.
compiler did you use to actually compile that bit of C code?
GCC 11.
You compiled it with GCC 11, and then you've already answered. I was going to say which C library did you link to?
Yep, that's my own C library. I've taken chunks of other libraries. It is up on GitHub, and people can have a look at it after this is finished. It is very shonky, but I just wanted something that worked. I didn't want to port a full C library.
That's cool.
All right. So I'm going to display what the this contains. So I'm going to do this. Nope, I'm not going to do this. I've got it wrong. That's the one I wanted. Yeah. So I'm going to run the utility that comes with this. It comes with this Pyromaniac that assembles things, and I'm going to match just the main function. So here we go. I mentioned that the standard compilers do not include function signatures. They don't, but you can botch them in because you can make it generate a bunch of NOP instructions that live just before any function, and then you can rewrite them with the symbol names. And that is all I've done here. It is a huge botch just to make things work, but I retain the ability to then have, this is a function called main. This particular branch here goes off to printf. This particular branch goes to printf. This one goes to clib version, and so on. It makes the code a little bit more accessible when you're trying to read it, and it makes backtraces work. So there's the NOPs that sit just before another function here. I don't know what that function is, but there's another function there that does something.
On other systems, is it putting symbols into the same executable or into a sort of manifest file alongside?
Usually you have ELF, so you've got the symbols in your ELF that you're not stripped most of the time, and that's where you get the information from. If you strip the symbol names out, then you lose them. That's usually what other systems do. And as said, if we were to switch to ELF as part of the standard executable formats, that would become easier. Yeah. Okay. Yeah, so that's basically that. Again, that's not particularly complicated in what it's actually doing. Yes, it's ARC64 code, so it's complicated, but that is what it's doing there.
Are you using your own linker as well?
I'm using the standard linker and a special linker script to link the files in a particular way. Again, this is all open source, so I will show people if they wish to see it when we get to the questions at the end. Is that okay?
Cool.
All right. Back to the scene. Right. So, quick summary of what we actually saw there. Has that moved on? Right. So, this is what we saw there. And what it's showing is that we can actually run things in a sensible way that were built with a standard C library. Sorry, standard compiler and linked with a C library. I've just described a little bit of how the C library works. I've defined this 64 to mean this is 64-bit, so it can ask itself. And the format of the clib is following the pattern that we established back on RISC OS 6. So, Hello World was the first RISC OS 64 program that I wrote, just to prove that it worked. And it validated that this was a sensible idea. The second one that I wrote was an animation using the draw module. It was a nice proof that the interfaces were usable. And the third was a little bit more challenging. So let's have a look at those. Come on, get me back to the right window. This one here. Share. Right, so. Right. PyroDev. Oh no, I actually need to share the whole screen for this one. Give me a second. Which window am I sharing? It is this one. Right. Hopefully people can see this now. We've got my entire window here. So PyroDev -wx command cog. So this is my animated cog that I created. And that's using draw, and that is all implemented in ARC64 using C. It was actually originally written in C and then run on 32-bit RISC OS, and then the code was made to work on 64-bit. But yeah, it's not particularly impressive, but it works. It's doing its thing.
The draw module presumably is still.
Sorry,
the draw module is presumably still 32-bit.
The draw module is the RISC OS Pyromaniac draw module, so it's actually part of the Pyromaniac implementation. I haven't yet got around to making either draw file or anything else work like that. I have only ported a single module to ARC64. Everything else is running in Pyromaniac, all the modules are in Pyromaniac, which is obviously in Python. But they implement the standard interfaces, so you can use these things without having the actual modules available to you that would be used on a native system. So if I actually show this, so if I do modules, don't do X. Yeah. Hopefully this is still readable. You can see that there are 64 modules already available in the system there, just because RISC OS Pyromaniac can already provide them. They're just there for us as we want to use them. The third program was a little bit more intense. It took me a lot longer to make work. I think, can't remember how long it took to work. I think was this 7 hours? I can't remember. But we can show this one. So here we go. Here we go. And hopefully this will work. Here we are. So this is Chucky Egg. Standard Michael Foot version, implemented in C from the basic version. And as you can see, hopefully, it is now playing. There is a game written for RISC OS, which runs on ARC64. And hopefully you can also hear that the sound works as well, because everything you get with RISC OS Pyromaniac, you get already. It is slow. It's RISC OS Pyromaniac, what do you expect? But it's working. That's cool. Sorry, I think that's cool. Again, source for this is available on GitHub. It proves that the graphics works. It proves that the sound works and that you get a whole bunch of extra things. If you saw the Chucky Egg that I posted on Twitter, that was actually the ARC64 version that was running, that I captured the video of. So you'd already seen it, you just didn't know. That was intentional. So let's return back from there to our slides. Where's the slides? Yeah, right. Come on, are you going to move? You going to move on? So, let's talk a little bit about when things go wrong. RISC OS Pyromaniac can report similar information for ARC64 to that in 32-bit, but it doesn't handle the exceptions properly. Not quite in the useful way. I just haven't got everything working. And it's still enough, even with that, to get a useful trace out when something breaks. I've got a crash program that intentionally crashes, and it tries to print a string at an address that causes an abort. And it produces output that looks like this. It says, exception report, fault address was 0. No, it's not. It was a read fault. Yes, it was, that's true. And it's given me the registers, but it's given PC correctly there. That's quite nice. And it's telling me that we are in the myPrint function, that we had print many was being called, main was being called, and underscore main was being called. That's because of the frame pointer being used correctly, and that's because the PC has been set to the right point. All of these things are still in flux. I haven't got the debugging part of this working very well yet, but there you are. it does do it. So, answering Andrew's question, they're all built with GCC 11 for ARC64. I use a Docker container that cross-compiles them. There's a little bit of magic that uses modifies the way that things work, headers on the files and some static linkages. But they're all publicly available. RISC OS 64 simple binaries and RISC OS 64 mfoot chucky egg. It's got the two things there. They've got their own C library, which is inside simple binaries. You'll find it in the clib directory. It's very simplistic, but it's enough to run all of those demos and other things. I chose these examples because it was useful to me. The earlier two showed that I could do things that were special to me. Chucky Egg was written by somebody else. It was something that was not designed to ever run on anything but RISC OS, but it also wasn't designed to be thought about for 64-bit, and it was convertible. It took me 7 hours to port Chucky Egg. I wanted to do it in about 4, but I got stuck. I spent a lot of time writing the C library. I spent an hour just cursing that I'd implemented kernel SWI wrong. I got the registers round the wrong way. But are those applications enough to show that 64-bit RISC OS is possible and you can get stuff working if you've got the inclination? Maybe, possibly, don't know. And there's more. If you've seen my presentations before, you'll know what's coming. This entire presentation was also run on RISC OS Pyromaniac, and the presentation tool was compiled for ARC64. And image file render module was ported to ARC64 and is providing the images there and in other places. We have modules, we have an actual application, something that you've seen being used to demonstrate things for the past far too long. Is that enough to show that RISC OS code can be produced from the original applications? Maybe. I've got a final demo where I can show you things. Let me just switch to the display again. I think it's this one. Yeah, hang on, I'm not sure. Yeah, it's this one. Yeah, share. That's where we were with Chucky Egg. So here we go. This is the demo. I'm not going to say much more.
You can't see this one, Jeff.
Oh,
on the Chucky Egg screen.
Yeah, I think you share the screen.
Let me share the screen again. Damn it, I pressed the wrong button. Let's hang on. Let me go and how very embarrassing. Right, share screen. Click share. Which one am I sharing? I've lost it now. Oh, come on, stop it. I was going so well. I was on such a roll. Not that screen, not that screen. This terminal here. Yeah, that's the one. Right. Can you see it now?
Yep. Yep.
Yes.
As I say, I'm not going to say very much. There you go. A final conclusion. So I've talked about what 64-bit is. I've talked about what's different. I've talked about what problems we have. And I've talked about how I have dealt with some of those problems. I've also shown you some examples of 64-bit RISC OS code running and how Pyromaniac can help and has done that. And with that, that is the end of my presentation. If you have any questions, if you want to talk to me, that presentation site is not currently there because I haven't got round to it. I only finished the slides at 1 AM. thank you very much. There's a lot of clapping there. That's really nice.
I did my best.
How do I unshare? Stop sharing. There we go. Thank you.
Thank you.
I think if that doesn't give everyone a kick up the backside, I don't know what does.
As I say, these are all up on GitHub. They're publicly available, so anybody can have a look at them, critique them, build them. RISC OS Pyromaniac is currently building it with the so it's currently using the sources on a separate branch so that it's isolated from the main code. It's not good. It's lashed together in some places, but that's also the way you have to make some of these things work. You try stuff, you see what happens. And part of this was I've been through like 5 different ways of calling SWIs and 5 different ways of handling other parts of the system, because I thought, well, I don't know what the best way is to do things. That is part of the process. I've described a lot of the things that I learnt and that were useful to me. Maybe they're not right. I mean, people have suggested various different ways that things could have gone that didn't even occur to me and that could have made things different. Please have a go, try things out, see what you can do. But that is where I am right now and how far I've got. Just so you've got some idea, I think it's about 3.5 months I've been working on 64-bit, sorry. Might be a little longer, but that's what I sort of have in my head anyway. Any questions, any thoughts, anything?
Yeah, I've got something, Joe. I'm just slightly confused as to what computer you were using for that. You were using a Mac, as I could see. Where is the AA64-bit computer running your code, and what is it?
So all of my code is running on RISC OS Pyromaniac. It's my operating system, and it's emulated through Unicorn. It uses an emulator to execute the 64-bit code.
Okay.
So that's how it's being run. Most of this stuff could be made to work on a more bare metal system. Part of the big problem is getting the low-level stuff up and working, which you can do. But Pyromaniac allows you to make the higher level stuff work. It allows you to make progress on building modules, progress on creating applications without having the rest of the operating system there, because, well, actually you have got that operating system. It's just not 64-bit ARM.
So you've now got a 64-bit Pyromaniac?
Yes.
Right.
So basically it's a development environment, isn't it? It gives you the enabler for test and develop, and as you say, you then go underneath it and then do the bare metal interface on that, so it's a bridge.
Yep, that's exactly what it is. That was all that Pyromaniac was ever designed to be, was just to be a development and testing system and to give you a way to play with things. You can try stuff out. I mean, the different way that SWIs are called, whether callbacks happen in different ways, you could try those things out. It's a bit difficult to change some things because they're embedded, just like on RISC OS, but you can play with these things.
I think that's absolutely fantastic, because the hardest bit is having an enabler to enable, actually enable you to play with things quickly. That's the point. That's the gearing. That's the general fundamental thing that acts as the brake in these things. So, well done, really cool.
Thank you.
Sorry, go ahead.
You talked a number of times in the talk about the need to re-implement the existing modules in C as soon as possible. And you also talked about how you've already implemented a lot of these modules in Python for Pyromaniac. Would you regard the work that you've done creating Python versions of these modules as a good starting point for people considering developing C versions of said modules? Maybe.
It really depends. So one thing that you'll always spot is the fact that there are really weird things inside the RISC OS way of doing things. And so I have chosen to do certain things lazily. But there are other parts that are just like insanely difficult to work out what's going on, and I've ignored, and I've gone just from the API and gone, this is what I've implemented. So the Python code would be way easier to understand. Maybe not exactly the same, but a lot closer. The important thing is that the external API look the same. So long as it looks the same or close enough, it doesn't matter to the user. So yeah, try that. Use either the Python code or the assembler code. If you happen to go, I don't understand what's going on here, I can look in one place or look in the other and see.
I'm just thinking that for a number of people, the Python code might be a lot easier to comprehend than 30-year-old Acorn assembler.
That is very true. Yes.
Somebody's asked about just having somebody having thought about it and read through one time, come up with you're describing what you think the assembler does. Exactly. You can compare the two against each other.
Yeah.
It's going to be
and there are also tests for many of the things that Pyromaniac does to check that the behavior is the same. I know it doesn't do the same thing for everything. I know it doesn't. But some cases it doesn't matter. At one point I had the implementation of, I can't remember. Was it the date and time I made come out slightly differently because it was never defined what it would actually return? And of course it could be different in different languages. And that caused problems for some things. And I went, well, fine. But you can play with these things. You can try them out different ways.
Yeah, Acorn managed to break something there because originally it was a defined format. And then when they introduced internationalization, they went, oh, it's up to the individual territory. Well, no, hang on a minute. The buffer is a fixed size. You can't just change what gets returned.
Yeah, so there's things like that you've got some limitations on. And those sorts of things could be like, well, that's not even deprecated. It's just not implemented on ARC64 RISC OS because, well, we don't want to bring across such bad legacy. You just return an error, and hopefully if you return an error then people will catch it. Probably not, but you can try.
Can I ask
or you could just return the correct value that is expected.
Possibly, yeah. I mean, that's always the thing. You could just go, well, I'm not going to use the internationalized version, here's the one that's there.
Yes, that would have been more correct.
Somebody else was asking a question, sorry.
In all this discussion of old behaviors and things, can I ask, have you considered, you obviously have a very thorough understanding of the APIs and how they connect together, and have you considered writing sort of emulation layer and running each, because this whole request of rewriting everything is a rather lofty one. And also someone used the phrase ornamental bars earlier, like it doesn't run the old applications, but it seems to me you are a hair's breadth here from having a layer which runs every module or every application in its own emulating environment. And actually, given the 64-bit ARM code is just not as elegant as the old 32-bit code. There seems to be merit in things living on in the 32-bit code as a bytecode format, essentially. So what about a multi-processor operating system, rather than considering the move from 32 to 64-bit ARM, but just considering it a move to a layer that allows applications written for any bytecode?
Absolutely. There's no reason why you couldn't do that. The focus of what I've tried to say is the moving things forwards. If you keep things back as just always the same as the old system, you're going to find it becomes a problem. But it is another transition method. If you want to do it through emulation, then cool. Think of how Emulor works. It executes many things, but it emulates some others. It provides it's a little bit easier for it, I know, because the instruction set is the same. But there's no reason why you couldn't do that. You could quite easily have a module in ARC64 that just shims its way into the emulation environment to provide the 32-bit modules. Why not?
I think what I'm saying is I think that's critical. I agree with you totally. You have to transition towards something. You have to be moving to a destination. And I've seen many projects in my professional career fail because everyone's just like, oh, and then everybody else will just rewrite the code surrounding this or whatever. And providing that emulation is like the thin end of the wedge. It would let you transition this over gradually in a more...
Yeah. I mean, I absolutely agree. But that is a that is a separate issue than the making RISC OS 64. It is a how do we transition things so that people can use whole systems. But that is an entirely valid thing. Maybe early execution on by switching the modes back to the execution state back to 32-bit, maybe doing it through emulation is the right thing. If you keep the same 32-bit model initially, that all becomes entirely transparent because your memory space is exactly the same. So that actually becomes quite doable, I feel.
I think that's it. And don't take my comments as negative at all. I think
not at all.
I'm so impressed by how much you have done. This is what I mean. Your hair's breadth from swapping out the layer that sits below things and defining, as you say, how a new 64-bit execution package would sit on top of that, which I would say is huge. I'm really, really impressed with what I haven't seen Pyromania before. I'm really impressed with the amount of work that's gone on here. But I want to see if it can be turned into a usable system.
Do bear in mind, Pyromaniac itself is not a usable system. You saw how slow it ran Chucky Egg, and that was on a pretty fast system. But the principles of what it does and what it's showing is useful. It is designed to be a debugging system.
Well, exactly. And if you had Pyromaniac's ability to emulate the actual real RISC OS draw module, then the speed, as you said, the speed of your development would increase hugely here. And yes, very impressive.
I mean, there's no reason why you couldn't have people writing a whole bunch of the modules whilst you're using them. It's like, yes, I'm re-implementing draw, and whilst I'm re-implementing draw, somebody's implementing draw file that uses it, but I'm just using the base version because we know that works. We can do that.
Yes, and I think, like I say, in the spirit of seeing the old 32-bit ARM as a bytecode, it's not necessary to rewrite everything. And this model where we recompile software to use other computer systems, I mean, the processors themselves are just emulating these instruction sets right, internally in the processor. So why are we placing so much value on the actual instruction set that we compile to? I don't believe personally that it's that valuable, and I think
I must admit, I mean, it's Jerf's party today, so I'm not going to bang on about this. I think that we shouldn't repeat the mistake of the past for the third time, when the 26-bit architecture, due to market forces entirely beyond our control, became no longer an attractive device. We decided that the way to fix that was to rewrite the operating system to be 32-bit. And then when market forces over which we had no control decided that 32-bit was no longer attractive, I don't think the answer is the same answer again, rewrite it now to run on 64-bit, because then when market forces over which we have no control decide that 64-bit is no longer attractive, what do you do then? Rewrite it again for the 128-bit? I think that given that that's not the way Android works, that's not the way Java works, that's not the way WASM works, it's not the way JavaScript works, viewing the 32-bit or 26-bit ARM as a bytecode in effect is entirely viable.
It is actually. I'm literally working on that, but you still have constraints. So your bytecode ISA is still what, 32-bit, 64-bit. You still have constraints. You need to work on things in a certain way. How are you going to address, for example, memory that is supposed to be future-proof 64-bit, but also 32-bit compatible, and all these things? It's too late to show you. I can just show you guys a quick demo thing working, but it's not simple. It's a lot more complicated, actually. For example, in my Ultima VM, the addressing is 32-bit, but you have a module ID that allows you to have 64-bit addressing in some sort of fashion that reminds a bit of bank switching, if you want. There's no bank switching,
Yeah.
no banks, but there has to be ways to be. You can compile Ultima even for RISC OS 310, and it works even on RISC OS 310 all the way. You have 64-bit on RISC OS 310 if you want, but it's the problem, Nemo, is you always going to have some constraint. The advantage is if you are happy with the constraint of a virtual machine, WASM, Ultima, JVM, whatever, then yes, you have exactly what you want and it's portable forever and you no longer care about the hardware. But that means that you accepted the constraint of the VM. For example, in Java, a 64-bit value already, because Java was not designed with 64-bit in mind. So a 64-bit value in Java is actually two 32-bit entries on the stack. So Java is already showing age, if you want. At least Ultima doesn't have this problem. It has real 64-bit values. But when we're going to have 128-bit, Ultima will have the same problem as Java. With 64-bit, right? So it's going to be 128-bit in two 64-bit value. So that's bytecode, right?
Yes, but our point is that we don't care about the hardware. So if the implementation is a bit ugly on a particular piece of hardware, so be it. I don't care. Next year I might have a different piece of hardware. Why would I care? I mean, you don't worry about that when you talk about JavaScript or WASM or even Android. You don't go, oh, well, hang on a minute. How big are these values on the stack? You just don't care.
Yes, you are absolutely correct, but you're talking about JavaScript. The bytecode has constraint, so then it becomes a game of compilers. I mean, we can discuss. I can even share with everybody the definition of how Ultima works, because Ultima has been designed. Because one of the problem is, why didn't I use the JVM? Why did I use WASM? Because they run really slow on RISC OS. They really are not designed for RISC OS. So I needed to create something that works smoothly on RISC OS. I had to start from the ground up. There are no other reason. I would never have done that if it wasn't for the existing RISC OS.
And what was that bottleneck? What did you identify as the reason for that?
They are completely against any form of cooperative multitasking. They are completely against any form of specific SWI calling and everything else in certain ways. They make a lot of assumption that everything is reentrant, so they work in a certain way. They don't have checks. They assume that they are working on a modern operating system. It's a very strong assumption. As a matter of fact, by the way, you don't need to believe me. You just try to run Java that was ported by Acorn on the RISC PC, check the CPU usage, even doing nothing, and it spins up to 100%. I show this to a number of people at the ROUGOL, and it's the same for a modern JVM that is just being ported to RISC OS 5. Same problem, spins the CPU 100%, doing nothing, just having a window open. Because there are assumptions there. And sure, you can patch things, you can do stuff around, but it will just cause troubles. You have other issues then when you start using these things. What about extending the operating system? What about, for example, having multitasking or RISC OS without the WIMP? Well, Ultima now supports that. What about multi-core support? Yes, it uses Jeffrey multi-core, so it runs on RISC OS, but when you compile it on Linux, macOS, Windows, it uses their own threading system. So you don't care in the bytecode about the multi-threading and the multi-core system, and that's a problem of Ultima, in the case of Ultima. JVM will never run with Jeffrey's multi-threading library. And so will WASM, by the way. I don't want to take too much time because the question should be for Jeff, for Jeff, sorry. But the idea of the bytecode works if you accept the limitation of the bytecode. Then everything as you said is absolutely correct.
The thing I would differentiate between is the whether you're trying to make a version of RISC OS that is just the 32-bit version, or whether you want to take RISC OS to a new place. That is really what I would say is the important thing there. I just want to notice that Cameron's got his hand up. Cameron, go on, you say your thing.
Hello. Okay, so actually, give me a few things from that. So I think on the back of the previous conversation, I think I suspect the main. I suspect for the most part. I suspect for the most. I suspect the main thing. I suspect there's a fair. I suspect there's going to be a fairly restricted subset of things that would actually be fairly restricted subset of things on RISC OS that would benefit from being able to use AArch64 direct. AArch64 directly. So A is hardware drivers and B is stuff where you want stuff like graphical rendering code or media codecs and stuff like that. So you could probably get away with a situation where you have 64, where you have 64-bit, where you have 64-bit mod, where you have 64-bit mod, 64-bit module. 64-bit module code, and then leave the application, and then leave applications in either real or emulated 32-bit mode.
So the sort of things you're talking about are things like the areas where you need some speed. You might think also cryptography. And other parts like that, where you want to do things in special ways, or where you've got particular libraries that are more specialized than the standard system, and that's entirely reasonable. You wouldn't want to just run them directly as part of the emulated instruction set, I imagine, because they're not performance critical most of the rest of the code, but they are, or they do something that is particularly special. Like, as you say, hardware drivers. And those sorts of cases, there's no reason why you wouldn't want to do that. I don't think that doing things through emulation all the time is the right thing. I don't necessarily think it's the wrong thing either. The need to actually produce something that works is really what you need. And do it how you like, whether you want to do it as an emulated system that executes bytecode, fair enough. I don't see much benefit in keeping everything exactly the same, so I'm less inclined to think that should work. But I do agree that keeping something that works is always important. Apple have always tried to migrate their users from one system to another through various emulation and translation systems. Yes, they dropped 32-bit support a little while back, and that hurt some things. But they provided good transitions for many of the applications, and it was only the things that didn't move regularly that it caused problems for. Proves that things can work. I mean, Windows as well also provided various emulation layers and evil hacks to make things work that shouldn't have done. There is a strong history of doing that. So yeah, I think that's a very reasonable thing to do, and to provide accelerated mechanisms for where you need to have that extra speed. Yeah, again, that's not where I was going with my presentation. It was purely to show that you don't have to only stick yourself into we're going to only have 32-bit. Unless you want to. If you want to do that, then you're not in my audience. But that was where I was going, was that I want to at least try and show, look, this isn't something we just talk about. This is something we can actually do.